Assalamu alaikum dear students, welcome to my channel. In today's lecture we are going to talk about a special kind of infinite series that is known as alternating series. Okay, so let's define this first. An infinite series in which terms of the series are alternatively positive and negative is called an alternating series. Okay, this word is most important in this definition. What is meant by this? It means that if the first term of the series is of positive sign, the second term will be of negative sign, the third term will be of positive sign, and this will keep going on and on. Okay, here I have mentioned few examples of alternating series, and if you notice, you can very clearly see that the signs are changing in every term, in every upcoming term. If the first term is positive, the second is negative, third is positive, fourth is negative, and so on. Similarly, you can see this from here as well. The signs are alternating. Okay, so such series are known as alternating series, and their behavior is very peculiar. Their behavior is different from many other infinite series. Okay, by the way, the first series that I have written here has a special name. Okay, and this series is known as alternating harmonic series sometimes. So let's explain their behavior. Let's see how they converge, when will they diverge. We are going to look at that in this video. So students, here we have the statement of the alternating series test. Okay, so what does it say? It says that if you have any alternating series, then this series will be convergent if it satisfies following two conditions. Okay, the first condition is that the sequence of the terms of series should be a decreasing one, and the second is the limiting value of this sequence of the terms of series should be 0. Okay, so let's check it out. If a series satisfies these two axioms, these two conditions, how will it converge? Okay, but let me take you back to the theory of convergence of series. How a series is said to be convergent? When will a series be considered to be a convergent series? Okay, our traditional way is very simple. We consider the sequence of partial sums of that series. Okay, if that sequence of partial sums is convergent, then we simply say that the given series is convergent. Okay, so we are going to adopt the same strategy to prove this, but in another way, in a different approach. We are going to consider not the whole sequence of partial sums, but we will consider first the sequence of even partial sums. Okay, and what does that mean? S2, which will be the sum of first two terms. First of all, we will consider it, then S4, then S6, and so on. Okay, so let's see how will it work. Now S2, as I have told you, is the sum of first two terms of the series, which are B1 and negative B2, and we know that this sum will be non-negative. How are we sure about this? Because we have been told that this sequence of the terms of series is a decreasing sequence. So if we take the difference of any two successive terms, our answer will always be non-negative. Okay, and then I consider the second term of the sequence of even partial sums, that is S4, and you people know very well S4 will be B1 minus B2 plus B3 minus B4. But the first two terms, B1 minus B2, can be written as S2, and the next two terms can be written simply like B3 minus B4. I have just replaced the sum of first two terms with another name, and that name is S2. Okay, and now this answer will always be greater than or equal to S2. How are we sure about this? Now S4 is made up of these two positive numbers. B3 minus B4 is also positive. Okay, or you can say at least non-negative. So it is made up of these two non-negative numbers. If you remove one of them, I'm talking about this one, the next number will be less than S4. Okay, and here in this case we have the number S2 here, so we can finally say that S4 is greater than or equal to S2. Okay, and in a similar way we can say that S6 is equal to S4 plus B5 minus B6, and this term will be greater than or equal to S4. Okay, I hope so. This is a very good and very clear concept to all of you. And now moving on in this pattern, we can finally say that S2n will be equal to S2n minus 2 plus B2n minus 1 minus B2n, and this will be greater than or equal to this term S2n minus 2. Okay, so this is the general you can say overview of all this work. Okay, so why are we doing this? We want to reach a conclusion about this sequence, and that conclusion can be seen from the line that I'm going to write it right now. Okay, can we say from all this discussion that 0 is less than equal to S2, which is less than equal to S4, which is less than equal to S6, which is less than equal to so on? What does it shows? Now this line is actually showing you that the sequence of even partial sums is a monotonic sequence. Okay, what kind of sequence is this? It's a monotonic sequence. So keep this in your mind, because I am going to use this in my upcoming arguments. So dear students, we have proved so far that the sequence of even partial sums is a monotonic sequence. Okay, now I'm going to write S2n in another form. Okay, have a look at this. Can we write S2n as B1 minus B2 minus B3 minus B4 minus B5 minus, moving on in this, and finally we will have Bn minus 2n minus 2 minus B2n minus 1, and finally B2n. I have just written the sum of first two n terms. Okay, and I have written it in a different way. Actually it was B1 minus B2 plus B3 minus B4 and so on, but I have arranged them in such a manner that this expression is valid. Okay, now you can see that very easily that all the terms that have been written in the brackets are actually positive. Okay, so you are taking everything out of this B1, and in result you get S2n. Okay, now what does it mean? Clearly it means that S2n is actually less than the term B1, because you are taking so much out of this B1 and then you are getting S2n, which means that actually B1 is greater than S2n, or you can say S2n is less than B1. Now guys, I want you to focus on this expression. What does it mean? It means that all the terms of sequence of even partial sums are less than B1, because it was a general expression. Okay, so what does that mean in return? It means that the sequence of even partial sums is a bounded sequence. Okay, our first conclusion was written here, that sequence of even partial sums is monotonic, and our second conclusion from this discussion is that the sequence S2n, which is a sequence of even partial sums, is actually bounded as well. We have already proved that it is monotonic. Now we have proved that it is bounded as well. And now I'm going to use a very famous result that we have already studied in our course, which is a bounded monotonic sequence is always convergent. Okay, a bounded monotonic sequence is always convergent. So if you are saying that this sequence of even partial sums is monotonic as well as bounded, so what can we say about this right now? This sequence of even partial sums is convergent. Okay, I hope so this is clear to you now, and let me write this right here. S2n is convergent. So this is our first conclusion about this sequence, but we have to check the convergence of the series. I'm talking about this one, which is consisting of sequence of even partial sums as well as sequence of odd partial sums, and if both these sequences are converging to same point, the same number, only then we can say that the sequence of partial sums is convergent, and that in return means that this series is convergent. Okay, so let's have a look at that case. Alright students, so far we have concluded that the sequence of even partial sums is convergent. Now if you are saying that it is a convergent sequence, it must converge to some definite number, and we say that we are actually supposing that that specific number, that definite number is S. Okay, now let's move on to the sequence of odd partial sums. Let's see how will they behave, whether they will converge to the same number S or not. Okay, so let me take the limiting value of the sequence of odd partial sums, which is S2n plus 1. Okay, now you people are quite aware of the fact that this can be written as S2n plus the next term, which is B2n plus 1. How? S2n plus 1 means the sum of first 2n plus 1 terms, and this can also be written as sum of first 2n terms, and then we add in it the last term, which is b2n plus 1. So this is equal to the s2n plus 1. Okay, so let's see how we can move on in this. Using the linearity of limit, we can write this as limit n tends to infinity s2n plus limit n tends to infinity of b2n plus 1. Okay, and from here you can see that limit n tends to infinity of s2n is s, so we have s over here plus. Now what will be the answer of this? Now we are going to use the second condition that was given to us. We have been told that the series that you are considering is satisfying these two conditions. So far we have used this condition, and now at the last step we are going to use this condition, which says that the limiting value of the sequence of terms of the series is 0. So the limit of b2n plus 1 as n approaches infinity, this will be 0. And finally we have s plus 0 is equal to s. So from where did we start? We started from here. We have taken the limiting value of the sequence of odd partial sums to see whether it will be convergent or divergent. And what we have concluded, that it converges. And to what value it converges? It converges to s, the same value to which the sequence of even partial sums was converging. And from here, finally, we can conclude that the sequence of partial sums for this series is convergent, which finally means that this alternating series is convergent. Okay, so this completes the proof. So dear students, I have made this figure to give you a visual explanation of what is actually happening to an alternating series which satisfies these two conditions. Okay, so we consider our first term b1, which is a positive term, so we move in the forward direction and we reach here. Okay, this is over s1, the sequence of partial sum, its first term s1, which is actually the sum of first term, which is the first term only. Okay, and then the second term comes into action, but this one is a negative term, so we will have to reverse from here and we will reach here. Okay, this is over s2, and then we add the third term, again we move in the forward direction, we reach here, this is over s3. So what you are seeing from here is that both the sequence of even partial sums and the sequence of odd partial sums are approaching to the same number s, which means that this sequence of partial sum as a whole is a convergent sequence, which finally helps us to understand that this series, the alternating series which satisfies these two conditions, is a convergent series. Okay, so this is the explanation of this figure. Please like and share this video, subscribe my channel and hit the bell icon so that you don't miss any update in the future. Thank you so much. It's a proven fact that generosity makes you a happy person. So be generous and please subscribe my channel, hit the bell icon so that you don't miss any update.